Welcome. I've been looking at the thermogravimetric data submitted to McFP4. Earlier this year, the peak values of mass loss rates were compared, and it was suggested that they might be used to assess variations between laboratories. I think we should be careful with that interpretation. Here I want to show that at least part of this variation might instead reflect the need for proper mass downscaling. What do I mean by mass downscaling? The basic idea is to make sure that TGA conditions are suitable for recording data of sufficient quality for kinetic analysis. Sample mass is only one part of that. Things like choice of crucible or purge gas and sample preparation also matter. Here the focus is on sample mass as a practical descriptor of sample conditions. The same powder was used by all institutes, so that reduces one source of variation. Overall, the procedure is straightforward. You start with a relatively large sample mass. Then you repeat the experiment under the same conditions but with a lower sample mass. Continue until the resulting mass loss rate curves are essentially in superposition. In this example, the 1 mg and 0.5 mg curves are nearly on top of each other, which suggests that further reduction is of little effect. I did not come up with this strategy myself. Mass downscaling is described in the ICTAC recommendations for collecting thermal analysis data. The idea is to begin with a suitable sample mass, repeat the run with a lower sample mass under the same conditions, and reduce the mass further if the curves still differ significantly. A link to this paper is provided in the video description. Now I come back to the original question. As an example, I am using the TUBS mass downscaling data that I have shown above. As of now, it is still part of a pull request, but may already be part of the repository when you watch this video. Here, the colors indicate the initial sample mass of each of the datasets. On the left, you can see the full curves. In the middle, the focus is on the peak region. On the right, the peak locations are shown. At this stage, the peak positions were taken simply as a maximum value of each measured array. Because the data are noisy, the trend on the right is not yet very clear. To reduce the influence of the noise, we fitted a third-order polynomial locally around each peak. The transparent curves in the background are the original data. The solid curves show the fitted peak shapes. Once a peak position from the fitted polynomial is determined, a much clearer trend appears. Lower initial sample masses correspond to higher peak temperatures. The same result can be shown even more directly in this plot, where the peak temperatures are plotted against the initial sample mass. Now the correlation is clear. The peak temperature depends systematically on the sample mass. So far I have shown the effect in a controlled mass downscaling series. The next question is whether a similar pattern can also be seen in the submitted interlaboratory data. Now let's have a look at some of the available TGA data in the McFP repository. I have chosen data for a heating rate of 10 Kelvin per minute, since most datasets available are for this heating rate. The main point is simply that the initial sample masses differ substantially between institutes. The data points below 120 degrees Celsius have been cut off because some datasets show an initial settling phase, presumably due to the release of moisture. The first points of each data series presented here are taken as initial mass for the following analysis. In the following plots, the same institute colors are used. Here the focus is on the mass loss rate peak. I fit a third-order polynomial to each peak, shown as the solid lines. This plot shows the extracted peak values. The fitted peak position lead to a tighter grouping than the raw data. Now also marker shapes are introduced so that each institute can be tracked more easily in the following plots. The marker colors have been changed to now represent the initial sample mass. A similar trend emerges where lower sample masses are correlated to higher temperatures. The marker shapes allow the comparison to the previous plot. Directionally, we can see the same trend as in the mass downscaling example. Even so, the absolute temperatures differ due to different heating rates. Still, lower initial masses are associated with higher peak temperatures. On the left-hand side, we see the mass downscaling data for a heating rate at 50 Kelvin per minute. On the right-hand side, the calibration data at 10 Kelvin per minute. In conclusion, if we compare peak temperatures between laboratories without accounting for the initial sample mass, we risk attributing part of this effect to laboratory variation. More generally, mass downscaling helps to ensure that TGA data are of sufficient quality for thermal analysis. That, in turn, allows for more meaningful comparison between laboratories and apparatus designs. The data that I have been using here comes from the McFP Git repository at the presented commit. You find a link to this revision in the video description. Thank you very much and have a nice day.